Greetings from IIT Kanpur. Earlier we have seen the process steps for making a standard canonical MOSFET, of course, with some frills in terms of taking care of some short channel effect like hot electron effect with lightly doped drain and so on. We saw some, but we saw the basic process. And interestingly, the MOSFET structure hadn't changed much for quite a few decades. There might have been small changes here and there, but basically you can make out when you look at a MOSFET. But interestingly, as things become more advanced and you continue to want to pursue Moore's law, that is, you want to pack more and more transistors, or put another way, get more and more functionality from the same size of the chip, it turns out that transistors have started to morph a little, change a little. This is a basic processing course, so I don't want to go very deep into some of the latest advances because some of them have not even been finalized. Maybe after 5 years they may take another turn and so on. But at the same time, it's important for you to be aware of the changes that are taking place. So I'll try to give a brief introduction in today's discussion. So we will talk about a glimpse of advanced FET structure and the evolution, how it is evolving. First, the disclaimer. This is going to be the outline of my talk. It's broadly divided into two parts. First, I would say how MOSFETs have evolved over time, and a very brief tutorial on why we need to do that. What is the short channel effect that we are trying to overcome that requires novel solutions, and the alternates that we are moving towards. You will get an idea. The basic idea seems to be that we had devices which are flat, source and drain were flat and on the surface of the wafer, but slowly they are starting to move into the third dimension, that is in the vertical dimension from the plane. A little bit of that. Following that, I would like to take a closer look at FinFETs. Among the recent structures that have come out, FinFETs already are in products. That being the case, it will be a good idea just to look at FinFETs. And also within the FinFETs, I would like to talk about how to make fins. Because this is a processing course, I just want to give you an idea how one can play around with the various processing techniques that are there and try to build newer structures. And the fin structure being a new structure, we can see the creativity at play. I will talk about at least a couple of ideas that are available today. So let's get started with a brief tutorial. Challenges in gate control of the channel as the gate length decreases. So this is classic textbook stuff. I have taken these diagrams from Euler and Cummins and Chan textbook. So if you look at it, the transistor is essentially source and drain. This is, say, it's an N MOSFET, doesn't matter, P MOSFET is similar. You apply the appropriate gate bias, you will be able to control the channel. And right under the gate, very close to the gates, that is the oxide silicon interface, you will be able to invert it, deplete it, or accumulate it. So you can make it more p-type, make it depleted, or make it more n-type. So you can do that by controlling the gate. And that is the whole game of controlling this transistor. But it turns out, while you want to control the region underneath, there are lots of extraneous voltage sources and supplies and potentials which can affect what is happening under the channel. One of them, of course, is the drain. Similarly, source usually is benign because it's at a fixed voltage. In an N MOSFET, usually it is ground, but you could always find an intermediate transistor where the source could also be non-zero. But essentially what it means is the drain voltage can end up affecting the channel here. So that's one of the things. So and as a result, what happens is you need to apply a larger voltage, or the threshold voltage can rather, it turns out in this case you need to apply lesser voltage in terms of the gate voltage in order to invert the channel, because the drain's effect is already there. The drain already has a depletion region, and that ends up requiring less gate voltage to turn it on. That means the threshold voltage starts dropping. So this is what you can see in the classic short channel effect. If you look at it, short channel effects, there are various features, but this is what, when you, by generically, if you want to say short channel effect, This is what it's likely to mean, but then there are many aspects of short channel effect as well. So the classic short channel effect, the gate length, if you look at it, for longer gate lengths, the threshold voltage which is shown in the y-axis is remaining constant. It's impervious to the channel length. It's not affected by the channel length. You make it smaller, larger, little bit. During processing, there'll always be variation, so it doesn't matter. But as the channel length goes down below 0.5 for sure, 0.5 micron for sure, this is micrometer length, you'll find that the channel starts rolling off. Okay, so what it means is, if there is a small process variation, your threshold voltage will vary like crazy. But not just that, your threshold voltage comes down. So that means you cannot turn off, many times you cannot turn off the transistor properly. So these becomes, because usually we use 0 voltage for turning off, so you'll find that you won't be able to turn off, there'll be a lot of leakage current. So this VT roll off, as it is called, VT roll off, is a big challenge. So people have tried all sorts of tricks. They try to increase the control of the gate of the channel. You try to dope this channel more heavily so that the drain will not affect much. You also make the gate oxide, which is actually the first thing people try, making gate oxide very thin so that you get good control. People can also try higher dielectric constant gates so that capacitance is more. We all remember that capacitance is epsilon A divided by D, right? A is per unit area, so it will not matter. So D is the, here is the thickness of the oxide, and the epsilon. So those are some of the tricks that they did. But with time, that may not be enough. So so you try to find other tricks how you can make sure that the gate bias that you're applying is ending up controlling the region of silicon in the channel, in the body of the transistor, and the drain and the source have very little effect, especially the source has very little effect. Another classic example of this short channel effect, as the device becomes small, can be seen very nicely with this potential barrier example. So if you look at long channel, this is a long channel. This dotted line is how the barrier is. So for the electron to go from source to the drain, if you have an NFET. Now, what you find is when you apply zero gate drain bias, this is how the barrier looks like. But when you go to high drain bias, which is something that you have to apply, because if you want to drive the transistor, you have to apply drain bias. So if you apply a drain bias, you find that the potential is distorted. This was the potential when VD was 0. When VD is high, it's coming down like this. Now, in a long channel effect, probably it doesn't show up at all, because if you look at it, the electron here does see this barrier, and there is nothing that it's not going to matter. So when the gate is off, it remains off. But let us look at what happens when the channel becomes small. When the channel becomes small, the potential on the drain and the channel will be interacting. So if you look at it, that the potential barrier looks something like this. Instead of being a plateau like this, it will look like a small hillock. Now, this is for drain bias 0. But as soon as drain bias goes high, you find that this comes down. So what do you find? The barrier for the electron is shortened. So what it means is, the threshold voltage that this transistor will see when the drain bias is 0 and when the drain bias is high is going to be different. So that's what is indicated here. Increasing VD, especially you'll find that when the channel becomes small, this effect will show up. This is similar to saying whether you are turned off the tap in your house so that the water doesn't flow from the tank overhead. But what if the tank level goes up? Then the water tap starts dripping. That's not fair, right? The tap should be closed irrespective of the level of the water in the tank. Whether the tank water is high or low, a closed tap should be a closed tap. Whereas here, what it means is when the level goes up, it starts dripping. That's what you're finding, because the barrier is less and it will start conducting. So that's not allowed. As a switch, when you turn off, it should be completely turned off. So clearly this is a big challenge, and this becomes a challenge especially when the gate length becomes tens of nanometers and so on, and so it becomes a big challenge. So people have tried various things. So let us see what you need to try. You can actually try various things to prevent the roll off as well as the drain induced barrier lowering. That's what it is called, DIBL. So you want to avoid this. So essentially what you need to do is, you should be able to control the device channel by the gate bias. So what do you do for that? People tried various things. They limited the volume that is there in the transistor. So they used a thin body transistor, but that led to some other issues because it was a floating body. So what they did was they ended up providing front and back gate to give better control. So what it means is this channel, I'll be showing with some diagrams shortly. The channel, instead of just controlling it from the top, you also control it from the bottom. So you have silicon with an insulator. So you have a top gate and bottom gate. So you are able to control the channel better. But even that doesn't seem to be good. So with time, people decided maybe we should go for vertical transistors. So this is where the FinFET came. FinFET is one of the configurations for vertical transistors. There were various groups that were working on it. IBM, Motorola, and Bell Labs, and IBM Bell Labs, and also Berkeley. And finally, the Berkeley group came up with the FinFET, which ended up being used eventually by Intel. And then following that, we find that as the transistors continue to scale, that is the whole thing about this technology, it continues to scale. So as you are reaching, say, 20 nanometers or something, you start using FinFETs. But what if it becomes less than 10 nanometers? Even that is not enough. So you have to go towards nano sheet type of devices, and this is essentially gate all around. Instead of just controlling from the top and bottom in the thin body transistor, in the FinFET you are controlling from 3 directions. In nano channels you end up controlling from all around. There are various names to it depending on the company which is making it. They all want to have their own trademark names, but essentially you know what they are talking about. So, and then finally, today's transistors, even that is not enough. As we are going to 2 nanometers and 1 nanometer, we might have to go for other approaches if you want to keep the functionality increasing with each generation. And so you have complementary FET, essentially N MOSFET and P MOSFET stacked on each other. So let's see what these words actually mean with the help of diagrams. So I have taken this figure from a review paper. There are many good review papers and many good material available on the internet as well for those who are keen. But this sort of captures what we are trying to do. So here on the top is the isometric view of the various transistors. So this is evolution of MOSFET over time. You have planar, double gated, FinFET, omega gate, gate all around nano sheets. This, and of course, as I said, complementary FET, which I'll show next. So this is how it is looking. But if you take the cross section view, which is what we want to look at, for the diagrams A and B, actually the cross section is in the plane normal to y. Okay, so in this direction is how the cross section is taken. For us here, for others ones, the cross section is shown along perpendicular to x direction. Okay, so if you look at it, this is the classic transistor planar. You have a gate with a gate oxide underneath, gate poly and gate oxide, and this is silicon. You have source and drain on 2 sides. You controlled it. Here, on the other hand, you have the gate and the gate oxide, gate poly, the thin silicon, and then you have a SOI, right? Silicon on insulator. This is the silicon that is sitting on the insulator, that is a buried oxide. And the bottom is again silicon, and you can control that electrostatically by putting a contact at the back. Of course, these dimensions are not to be scaled, it's not to scale. The top film may be of the order of 100 nanometers or something, whereas the bottom can be of the order of a micron also. So, but all the same, electrically you have good connection. So this channel that is there at the top, you are controlling from the top as well as from the bottom. Okay, so this clearly gave better control of the channel compared to the planar structure, but that was not enough. So what do? Can you get other directions? So what they did was they tried to build these fin-like structures that is sitting on the substrate. And notice the source and the drain are in this direction. The gate is wrapping on 3 sides of the fin. Initially, they just were using the 2 sides, but eventually they use the 2 sides as well as the top. Why waste the top as well? So you have a thin oxide, gate oxide all around this fin. On top of is the poly, which is patterned as is shown. This is what is the FinFET. The cross section of this is shown here. If cross section is taken, as I said, perpendicular to x in this case. So now this is good, but again, people, what about the bottom? So if you can get a better control of the volume if you can also encroach in the bottom side, which is actually electrostatically connected to the body of the transistor, right? You can bias it with the well and all that, but still that is a challenge. So then they went for gate, omega gate. So essentially you do some undercutting, but it is looking like the Greek capital Greek letter omega. So, so you have more than 3 sides control. But then why leave it that way? Why not go all around? So you have a gate all around. GAA stands for gate all around. So this was how it was envisioned. And indeed, that's the direction it has taken. Instead of making it circular, what they did was they just turned these fins in this direction, made into narrow ribbons, nanoscale ribbons. And the nanoscale ribbons have, as you can see in the cross section diagram, a thin oxide all around with gate poly all around. So when you are contacting it, the silicon which is running in this direction under the gate region, around the gate region, that whole volume can be controlled very nicely by the gate. So this is how they went about making the better control. So this way the short channel effects are the leakages that came as a result of drain. Whenever you turned it on, you had started getting leakage, you could minimize it significantly. And this indeed is now one of the front end research work, and many of the development projects and others have already been demonstrated with this. So for production, maybe some of them are getting slowly into production as well for this ribbon FET. Now this is it turns out is not enough. It is because what is happening is Moore's law requires that you have functionality keeps increasing. So one of the tricks that people have done is, instead of using one transistor, can we have multiple transistors? So the initiation has been made. Now this is not something new. People have thought about stacking transistors in 3 dimensions for a long time, but it brings with it a lot of challenges, as we will see in the next slide. This is how they have tried to make the stacked transistor. So there are a couple of places from which I have borrowed these figures. This is from Spectrum, and this is from techovedas.com. They have talked about Intel's breakthrough technology. Some good summary is there. You are welcome to check these out. So typically what you do is you have a P MOSFET. On top of it, you build an N MOSFET. It turns out that today's technology allows it. And also, some of the tricks that they do is they make the P MOSFET with silicon germanium or germanium itself. On top of it, again, bring back silicon. They use such tricks. Of course, trained N MOSFET and compressed P MOSFETs are also having advantages. So actually, you can use strain also to change the mobility in these transistors. Now, you can see you have P MOSFET and N MOSFET. So essentially, it is like a NAND gate or NOR gate, how you, depending on how you connect it, and they are built on top of each other. And today they are able to do this. Look at the connections. If you want to get this connection, you have to come this way. That top connection will come this way. And then supposing I want to get the source and the drain on the 2 sides, they are to be connected separately on the 2 sides. So it's a big challenge. It's a big nightmare in a sense. That's what people thought. But the interesting point is, as Samuel Moore, one of the editors of IEEE Spectrum, he puts it very nicely. The big 3 now can make CFETs. So that's the next stop in the Moore's law roadmap. So this was 2023 itself. IEDM, all 3 were able to demonstrate. All 3 major manufacturers, that is Intel, Samsung, and TSMC, have demonstrated these stacked FETs. So it's a question of time before which it comes into production. They are quite confident, and they are going on developing it to make it production worthy. Why production worthy? Because it's not just about demonstrating one device. It's not just demonstrating one device. If you have to make zillions of devices. You make devices all over the wafer. You make devices over multiple wafers. So it's actually it has to be an extremely stable process, and you should get sufficient yield. If you make 100 and you get one device, then it's not going to be very economical. If you make 100, you should get as close to 100 as possible, typically 90. These numbers are not revealed, but that's where the competition is. The higher the yield, higher lower will be your cost. No, easier it will be to play off the competitor with the customer by offering lower price. So this is what it is. And now this is the how it looks like, schematic of it. Now one point I want to bring out, if you look at this silicon pillars or ribbons, in this case ribbons, it's not easy to contact them, and if you contact them, their series resistance can become very high. So they do another trick. They actually grow silicon or silicon germanium around this epitaxially. So the originally they have this ribbon, this structure that I'm showing on the middle of the page. Then on the right side is what it will eventually look at, because these green and the blue that is there, they will actually be epitaxially grown. The reason they are looking different is because they are of different orientations according to the need of the P MOSFET and N MOSFET. You want to maximize the performance of that. Typically, nowadays the mobilities of P MOSFET and N MOSFETs are coming close to each other. But that being said, if required, you can adjust the number of ribbons to be more or less on whichever has lower mobility. Typically, PMOS has lower mobility, so you could have more number of ribbons for P MOSFET if you want to make the P MOSFET and N MOSFET balanced. Now, one advantage of this is you can use it as an inverter, because as inverters you need P MOSFET and N MOSFET. We have all studied that in circuits. So that's a basic structure for digital electronics. So it comes as a package. Of course, you can also use individual transistors, but then connections and other things you have to watch out. So I hope you got a glimpse of the direction in which we are evolving. This is the key takeaway on transistor evolution. So if I may summarize, MOSFET gate length as it shrinks gives rise to short channel effect. We have been grappling with it for many decades actually, and typically earlier solutions were easy. We were able to handle it. But today we are having to take radical steps, because we want to get good control of the channel with the help of the gate. So this is done by trying to make the gate surround the channel region, and that is the only way you can do that. So there are various ways in which it evolved. First, it was of course dual gate from the top and the bottom. Then they went to using fins where three sides they were surrounded. Then they went all around. And then of course today that's not enough, because you want to pack more. So if you're now putting two transistors in the place of one with a complementary FET, so that way you double the density in one go. So but then of course it comes with a cost of challenge of building it and challenge of connecting it and so on. So this is the current trend, and this is likely to come into market maybe in the next 5 years or so. So please note that in all of this, newer methods keep popping up. There's no limit to human creativity. People keep coming up with newer and newer methods, and not just that, newer materials are also brought in. Many times you will find that the material that you used may not be appropriate for the new structures. For example, when you use copper, you have multiple linings. You need to have, as we already saw, tantalum and tantalum nitride, and then tantalum nitride, tantalum, and then we had to have copper seeding and so on. But when you scale it and bring it to small dimensions, that may not work. So you may have to go for newer materials. You might have to go for material like cobalt. I hear ruthenium is also something that people are actively looking at. So people have been looking at, so new materials and new methods, they keep helping us march ahead with the advancement of electronics, which seems to and the demand is also ever growing, especially with artificial intelligence and the need for huge computing power. It appears as though the demand is only going to increase, and that has been satisfied thanks to the creativity and innovations of the device engineers as well as the material advancement. Now we move to the next part of today's discussion. Here I would like to talk about FinFETs briefly. I would like to give an overview of FinFETs so that you are familiar with what is what. When somebody discusses or you see something in a paper, you understand what it is. And also we'll talk about one aspect of the FinFET. There are many aspects in FinFETs where things have evolved and become more sophisticated, but the most obvious thing that is different is the building of the fin. Earlier everything was in two dimensions. Now you have a fin that is jutting out, which is narrow and tall and long. So how to do that? So that's so I would like to give one aspect of the fabrication just to give a flavor of how process engineers and the type of things we are trying to learn can bring out creativity. It's like art. You are taught the basics, then you can, in the context, you can come up with newer and newer stuff. So, and it's a lot of fun. So let's take a look at those aspects in this such segment. So first, I would like to show the structure of FinFET up close. You have already seen it. You have silicon substrate. On top of it will be oxide, and somehow the fin will be jutting out. And at some point of the fin, you will put the gate poly on top of a thin oxide that is formed around the fin. This is how a classic FinFET is structure is supposed to be. But notice here that in this classic structure, and which is what Intel ended up using, you have silicon substrate and directly it is touching that. So this is how it is done. Now it turns out there were lots of groups which were also using silicon on insulator. That is, you had this thin crystalline silicon on a complete insulator, as is given in this case. And in this case, actually the fabrication process might be to some extent simpler. That is, you have this thin silicon, you need to just pattern this into a fin, and you don't have to worry about etch stop and all, because the oxide is there. Silicon and oxide, we can easily have a differentiation. Selectivity can be quite good in the etching, and then of course you do the rest of the pattern as in this case. But it turns out with SOI, when you use, while it's easier in processing and you do save some money and time, but then making of the SOI itself has some investment. So it's a game that the business people will have to play to find out what is optimum for them. If you can get some really high quality but very low cost silicon on insulator substrates, this would be the one. Otherwise, this may also work, as some companies have followed. So I hope you get a feel for how the device is. One side of this fin is source, another side of this is drain. Of course, all MOSFETs are typically symmetric, especially because you may need it for pass transistor applications. So typically you want to keep it symmetric, and also of course easier for fabrication. Now at some region you have a thin gate oxide, you deposit the poly and you build it. So if you look at it, it is not just a single fin that can be built. As I said, this is the traditional, as we have already seen, a traditional device which is flat. All that you did was this channel region underneath is actually going up, and of course when it is going up, you need to make the source and the drain also follow that, so that you can get electrical contact and continuity, and then of course the gate around it. Now nothing stops us from limiting to one fin. For a given transistor you could have multiple fins, so why not? So that's what people do. Now what is interesting, so if you want to make a larger W transistor, all that you need is you have to decide how many W's you want to take. Notice here that W thus becomes discretized, right? Even earlier in a regular design also, they won't allow you to go to arbitrary lengths. You typically go for, say you have a minimum length, then you can go double of that or 1.5 that. You cannot say, I want to make it 1.3654 times W. You cannot do that. You have to go for a fixed number. They discretize it, then that's how designers do the design, because of convenience and practicality also. There's no meaning after some, because there's a lot of variations that may come. But in this case, even the W itself, the transistor itself is discretized. So it's like having multiple transistors which are put in parallel. So you have transistor 1, 2, 3, it behaves almost like, it behaves like that with a common gate, and of course you can have a common contact, as we will see in one small figure that I have later. So, so if I want to make larger W, and I just need to have more fins. Now, one of the key things in this is, if I have a few, let's say 2 fins, now the space between the fins will end up making the size of the transistor larger. So you want to make a smallest transistor has a given size, but if you have two fins, depending on the spacing that is required to get two fins, to build two fins parallel to each other, the variable is called pitch, as we will see shortly. So that spacing will determine how compact these large transistors are. So this FinFET or three-sided around 22 nanometers or so, Intel started implementing it in 2011, and around and later when they went forward, many times the next generation, all that it did was it brought these fins closer to each other. So for example, if I'm not wrong, 14 nanometers and 11 nanometers, one of the main differences is that the fins came closer to each other. You are able to implement it very reliably next to each other. So that's one of the key aspects of this. So I hope now you have a feel for what FinFET is. Having seen that, let's see what are the parameters of FinFET that people look at. So this is a simple diagram. This is a diagram I borrowed from Professor Sujay King's presentation. So you have the source and drain on the fin, and at some point there will be the gate, and there will be a thin gate oxide all around it. Now there is something called a width of the fin, that is this. Remember that width of the fin is different from width of the transistor. Width of the transistor would be this length around it, whereas width of the fin is this. Height of the fin is this, and of course gate length. And there is another parameter that is very important, the pitch of the fin. What is the minimum distance at which you can put another fin to make a reliable transistor? Remember that there will be lots of bells and whistles that will come on this. There you will have spacers, you will have contacts, all sorts of things will have to be built on this, right? So what is the minimum that you can do? And this pitch plays a very important role, not just to make it compact, but in terms of reliability of, as I said, when you are actually processing it. For example, if I want to dope this source and drain, after the fin is built, you have to dope it by implanting from the sides. Now, if there are many fins standing next to each other, then there will be shadowing effect. This is similar to multi-storied buildings kept next to each other. In fact, certain cities have rules how close these buildings can be, because they want to make sure that people below get sunlight, and also of course safety and various other factors. So this distance between it is controlled by various subsequent process, will control various subsequent process parameters, and maybe even limited by that. One of them, as I said, was, for example, if I want to dope this fin, I have to dope it at an angle from here. So when I'm doping this first fin, the second fin will be shadowing it. So you have to make sure that what is allowed and what is practical. Now let's look at the transistor as now. Transistor gate length, as we see, is this. Okay, the length of the fin will be this long thing, but transistor gate length will be this width of the gate poly that is all around this fin. Okay, this you deposit gate poly all around, and then you etch them away using lithography, so you get this L. Now what is the W for this? That's very interesting. It will be all along this, so H one time, and then all along the top, that is W one time, and then again H all along. So it will be, W will be, for a single fin will be 2HF. HF is height of the fin, plus WF, that is width of the fin. And if you have n parallel fins in a particular transistor, as is shown, remember this is a common gate that is touching all of this, and similarly you will also eventually make the source and the drain linked to each other. You can do that. So this is the W will be 2H plus W times N. So this is the number of this is the W for a transistor where the number of fins is N. So clearly the device performance can be achieved, and the packing can be increased by doing a lot of things, but layout efficiency is also a big challenge. So you want to, it's a trade-off. You have to be careful not to be too aggressive in trying to do what is practical for one aspect, because it's the full device and the system that has to work. It is not just one aspect of the processing. Now let's take a quick peek at the layout of how this would happen for a FinFET. So this is our classical transistor. So this is actually, they are trying to save space. So what they are, instead of making a long gate, what they have done is the center part they have made the drain and the source on the two sides. So this is like two transistors in parallel. So such ideas have exist already, not just with FinFET, but even earlier. You try to minimize and make it into a regular shape, right? Instead of a huge long transistor, you can make it into a more squarish shape by using such tricks. So this is a flat device. This is the bulk silicon that we are all familiar in terms of layout. Now, how will it look like for a FinFET? It looks like this. And notice, and similarly here you have drain, you can do a very similar thing. Now, what is interesting here is, as far as the layout is concerned, not much difference. There is a difference in terms of the number of discrete fins that you can put in order to get the number of W. If I want to increase the W, I put more fins, right? So, and of course, it should be put as per the pitch, which is determined by the process people in consultation with the design engineers, but the process people have the last word in terms of how close they are willing to bring it together. Design people will want to put it as much as possible close to each other, but practically there are limits, so that's sort of fixed by that, the pitch that we saw. So if you look at the layout, not much difference. So that's very heartening, right? And of course W is quantized. That's something that, of course, that's a design rule that can be given to a design engineer and they can implement it. And this is an image of the thing. So these are the various fins, gate, and then and you have the source and the drain on the two sides. So this is how it would look like. Now I got another image which I picked up from an early journal. So you notice these are the two fins, but so you have the source, supposing these are both sources, right? So you can connect this by epitaxially growing silicon all around it, and that way you have this is only at the source side. Remember that under the gate it is remaining as it is, and similarly on the drain side also you can epitaxially grow this. What is the advantage of this? It's much easier to make an electrical contact on this, and as a result the series resistance to the source and the drain contacts are much lower. That it's important, as anybody who has done device physics and has some basic idea of device modeling will know, the source drain resistance to a MOSFET is very critical. If they go high, the voltage that you are applying will end up at that point, and it will be hurting you both in terms of the gate voltage that you are able to supply as well as the drain voltage you are able to supply. So that it's a good idea to make sure that you are able to give a good contact. So you actually epitaxially grow this. So these are the power of modern processing, and it's amazing how they do it reproducibly over millions and millions, actually billions of transistors today on a single chip, and there are billions of chips that are made. Okay, so this is mainly for improving the source drain contact. So this is how it will look like. You won't be able to actually see the fin at all. You'll be able to see something like this. Okay, so now we saw the basics of the FinFET, and I hope you will be able to recognize a FinFET when you see one and understand what is happening, where the source is, where the drain is, what the gate is, and so on. Now let's look at one aspect of the FinFET. The fin is one of the most distinct feature of the FinFET, and it turns out that you want to make it much smaller than what lithography will allow you. So what do? There are lots of tricks people use. Of course, you try to push the lithography limit as much as possible. That's one way, but you could also use other tricks. So I will be highlighting a couple of process methods that people are using. One is a subtractive method, which probably is an intuitive method using lithography and so on. And then you could also use a replacement method. Okay, so actually this allows you to make even smaller dimensions and closer pitch. So let's go start off with some processing, basic processing. So we start with a silicon substrate, as we did in earlier cases of process examples. So first thing that you do is you lay the layers that are needed to make a hard mask. So as you remember from the earlier two discussions on PN junctions as well as the MOSFET, the CMOS process, you have to go a thin layer of oxide. This is usually a buffer layer, which you want to, on top of it you put nitride. Why don't you put nitride directly? because nitride directly on silicon during thermal processes can cause stress, and even while depositing it can end up causing stress. So you want to make sure that you are able to put this. So you have thin oxide and then nitride. You use this as a hard mask. So you do photoresist. With using photoresist, you do photolithography. Now this photoresist and lithography, there are lots of tricks people have been trying. Double photoresist, that is, the pitch is often the limitation. So what you do is you have this, and then second time you come and again do photolithography by doing exposure at this point and this point. So these are some tricks that they use. And then there are many others, optical proximity correction and phase shift mask, all sorts of tricks they use to bring this size as small as possible and these things as close as possible. You want the fins to be next to each other as far as possible. So once you have done that, we have seen how to do the hard mask. With the help of the photoresist, you etch this nitride and oxide, and once that is there, this nitride and oxide will be a hard mask. Photoresist also can be used for etching, but during etching, photoresist also gets etched a little bit, and if you want to get a deep etch and a vertical etch, it's a challenge. So that's why you go for a hard mask. So when you do this, you get pillars. We have seen a similar structure earlier, if you remember, shallow trench isolation that we saw. It's very similar process. You try to make this as narrow and as deep as possible, and of course by using this lithography tricks, bring this as close as possible. Once you have done this, now you can remove the mask, hard mask that you put, nitride and oxide, and you get something like this. In this state, remember, this is going perpendicular to this fins are structures which are coming out of the plane and going into the plane, right? They are vertical in direction. Now if you want to dope this well, what I do is I dope it now. I can dope it at an angle so that this region gets doped, and especially the bottom of this gets doped. So this is where you want to make sure the distance is properly controlled. I have not shown the doping and all that. I just wanted to show how the fin is made. And then following that, you do another string. Once the well doping is done, you fill the whole thing with oxide and then etch back the oxide to a desired length. So this is your classic structure. So you have fin 1, fin 2 and all isolated from each other by a thick oxide. Of course, in these regions, you would have done the well doping in this stage. So this is how a fin could be built by the subtractive method. But what did we see here? There were limits on what's the size of lithography and how close we could bring it. So then the people, creativity, there is no limit. So they started doing something else. They went by the replacement method. Here what you do is, you again do some pattern poly. This is very similar to the gate structure that we did in our planar structure. So you have a thin oxide done, deposited, then you deposit polysilicon and pattern it. Again you push your lithography to its limit, okay, and then you are going to use this to build what is this structure is actually a mandrel. Mandrel is essentially a structure that you use when you are doing lathe and something as a placeholder. So you use it as a placeholder, maybe to measure how much you need to chip away the metal or something, and then once the metal is done, you just remove the placeholder and then again use it again for next one, right? So that's what is called a mandrel. So this is actually a support structure that you are building. Once you have done that, you might remember this figure from earlier process, although it was built for another context. So this is polysilicon oxide. You can actually build spacers. How did we build the spacer earlier? We deposited something and then etched anisotropically from the top. So if we remove equal amounts, at the corners some amounts will remain. This is known as a spacer. You can see this is very similar to when you are sweeping, say, and there is a step. You'll find that dust will collect at the corners, right? It's very similar to that. So here the oxide or nitride has formed in these corners. So you deposited it on top and you etched it, as we saw earlier also. So then you get this spacer structure. Now these spacer structures, mind you, can be very narrow. much narrower than what you can achieve with lithography. And not just that, because these are next to each other, notice earlier there were, if lithography allowed you to get 2 masks, in this case you get 4 masks here. How? You remove this, this is the mandrel, right? You remove this thing by etching, and then using these spacers as a hard mask, you etch down. Okay, so the hard mask that you built by photolithography earlier is being built by building a spacer around the gate structure here. So it's a really neat and cool idea, where you are able to get 4 structures where earlier you could get 2 structures. So you are able to build 4 pillars next to each other. So do you see the advantage of all these various processes? You bring in where nobody would have thought that that would play a role. You bring it in and you are able to get a very interesting structure. So using these spacers as the hard mask, you do this. Then of course you can remove the spacer. You do the implant as before for the well structure. It's very similar now. And once you have done the well doping, you can actually fill the whole thing with oxide and then etch back to this level. So this is the classic structure of this. Then of course you on top of it, you deposit the grow the gate oxide, deposit polysilicon, and define the gate length by patterning the gate poly in the direction perpendicular to this, right? So so perpendicular to this, so gate length will be in that direction. So now you have got an isolated fin. So I hope you are able to see, if you are being creative, you can actually come up with a different way of getting the same thing with the existing resources. Mind you, lithography has not changed. With the same lithography, but we saw some similar structures earlier, using those in this context to build a different a closely packed structure, a same structure but a closely packed structure. So this is how fins could be built. Creativity is continuing, and as we speak, people are developing better and better ways of doing stuff. And of course, as we saw, it's not just the fins, you need to have ribbons now. You need to turn the fins around, and then you need to stack them up. So processing is going on, marching forward, and we have to keep our eyes and ears open to be willing to learn anything new that is happening. So let's take a look at the takeaways about FinFETs and fins. What did we see in this? FinFETs help overcome short channel effect to some extent. I say to some extent because now the demand is even more. So you have to go for a gate all around. So FinFETs significantly helps overcome short channel effect. And the layout of transistor is similar. If you look at as design engineer is concerned, the rules were given to him or her in the same way. The width, of course, is quantized in FinFETs. The fin width, height, and pitch are the key parameters for the fin. They end up defining to some extent the W of the transistor and the size of the transistor. The L of the transistor, of course, is by patterning the gate poly on the fin. You need to build tall, narrow, and closely packed fins as much as possible, but it's a challenge. And as we saw, replacement method gives finer dimension, and you use the mandrel, and around the mandrel you divides some structure, the spacer, and using that you could get taller and thinner fins. But they are difficult to handle, but they are handling. The various fabs are handling, and they are able to reproducibly make it. So it's amazing that they are able to do it, and hats off to them for their ability to do that. The space between fins, of course, ends up being limited. We can make them maybe smaller by bringing more creativity, but sometimes some subsequent processes, for example, as I gave an example of angle implant to form the source drain, or to form the well implant first, and then after the gate poly is put to make the source drain also, you need to do angled implant. It has to be possible. So clearly there are lots of challenges in processing, and what is interesting is, and this is where I think we should never say no, right? What is interesting is, with ingenuity and bringing in ingenuity from other areas, in this context especially from materials and processing and chemical engineering and so on, if you can bring those ingenuity together, you may end up being able to fabricate more and more novel structures in the coming years. And I'm sure creativity is certainly going to blossom even more. and maybe some of you will take up the challenge. Thank you.